Sorry about my voice. I'm just recovering from a flu. It was really a man flu last week. But anyways, today we basically have the second part of the filter design. Last week we have the FIR filter design, which is finite impulse response system, which is based on basically defining a impulse response such that the system behaves as planned. And as you remember, of course, everyone remembers this one crystal clear. We have this kind of window, a design window. So the from 0 to sampling rate over 2, the low pass filter design box looks like this. So we have the cutoff frequency, we have the stop and start frequency, then we have the passband ripple. Well, this is actually 0 dB here. So the ripple amount of ripple on the passband, and then the stop band attenuation. Those are the parameters that actually define a low pass filter. And last time we were designing the low pass filter using the the windowing method on the windowing method. The reasons to use FIR filter are basically that it's always stable. Another one is linear phase response, meaning that, for example, the really time critical applications, meaning time critical in sense of time difference, time delay. If the time delay must be constant, then the FIR filter is the only way to go. And another one, of course, is stability. If it's a higher order filter, then basically even if you start having some computational issues on your system, you still have chance of having a filter instead of oscillator. Okay. So let me go to the slideshow. So basically, I didn't call this one filter design IIR, but filter design 2, because basically I'm also mentioning a couple of other things which are not actually the type of the IIR. Okay, let's see. I don't know. Okay, there we go. So a few properties that come with the IIR filter. It's never linear phase. It can be close, but never exactly linear phase, except if it's 0 phase, but that's basically not actually a filter. It's more like the implementation. Any filter can be 0 phase shift filter. You just reverse the time of the middle and run it twice through the same system. But IIR filters basically have better amplitude response with lower number of calculations. So this is more cost-efficient filter type. So actually this is quite natural, since in case of the FIR, we basically just have the, if you take a look at the zero pole plane, we have all the poles at origin, and basically we are just having these locations of zeros to tweak the amplitude response, meaning that in here, to flatten the amplitude response, we need to add actually some extra 0 pairs like that, not just the complex conjugate pairs, but also reciprocal pairs. I'm not going into in details of how to prove it, but that's basically the case. But anyways, that's how you basically get the amplitude response these zeros go like that, but then how to flatten originally that one is you put some attenuation and attenuate this so that it actually falls like that. Okay, so that's the way to flatten the passband attenuation on the case of FIR. On the IIR, basically, if you do the same thing, you need by default less poles, because instead of this effect here, you can actually put the gain in here, meaning that, oops, is there somewhere a trash bin? Oh, yes, of course there's a trash bin. So if we add the poles like that, we have actually added only 4 poles instead of 8 zeros. And that will basically do the same thing, but with gain, flat response on the passband. Okay, so it's more cost efficient way of getting the passband flatness. Applications, okay, now we are basically talking about lots of commercial applications like any audio filters. Audio doesn't really care about the phase response because there's always the, what is that called, wavelength dispersion on air, meaning that different frequencies on sound are actually traveling in air in different time in any case. So phase difference does not really matter much. Equalizers, so adjusting balance between frequency components, that's one application. Feedback reduction, yes, feedback, actually it's echo, that's a feedback. If you want to do the reduction, then you basically just have to find the correct echo time and amplification, and a very simple filter itself, but it's a little bit complicated to have it tuned. But anyways, the echo reduction is a simple IIR system. Okay, then again, another thing, high Q factor filters, meaning how to make really sharp filters. Okay, this is not messy enough, so for example, a system like that would have a peak response on that frequency. Okay, and then some others application areas. The caveat on this one is a complex design methods. There is one very simple that you can pen on paper. Then another one actually which is using this, which is more or less transforming an analog system into a digital domain. And then they are the way to go. So direct design, the third one there, is the easiest one if you can do it. Meaning that we just put these zeros and poles on the correct places and that's it. Okay, direct design is impossible for, say, more complex systems, or if you really want to have exactly flat passband requirement, then you need to actually do some calculations. Then there's this bilinear transformation, which means that we basically take an classical analog filter like Butterworth design, and they just use simple replacement of S equals to 2 over Ts Z minus 1 divided by Z plus 1. That actually transforms a analog system into digital domain. It really makes a, say, huge warping of the frequency space. Okay. So, yeah. But it works. And it's guaranteed to have a, if you have an analog system which is stable, then this gives always stable system also on digital domain. So that's one way of actually to go, but well, it's ancient method. What I'm always recommending having a tool that has some optimized methods there or already installed and then just use those. Then there's the parametric modeling, which is basically just a well, not really curiosity for you, since think of a complex analog system, but you have paid, several weeks to work on the S domain, not actually S domain, but differential equation. So differential equation is basically just, it's easy to write differential equations. It's just plain physics written in equation form. And then it's very easy to replace the time derivative with delta x. Instead of differential of x, you put a delta, meaning the two subsequent samples, and then divide by the sampling rate. Guaranteed to give a system, which may or may not actually be close approximation of the real one. This has the same problem as the truncation of the impulse response. Exactly the same. So this actually does aliasing of the spectrum, meaning that you will always, it will fail if this system is a kind of fast responding system. But if your sampling rate is high enough, then why not? It works. Okay. And directly to the only filter you can design with pen and paper, starting from zeros and poles. It's a band stop notch filter, a simple filter. You have 0 and 0 on the unit cycle. Maybe I should try. I will draw another. You had pictures, right? Did you already have pictures? Yeah. Okay, good. Maybe I'll continue here. Complex pay. And then let's think that this is a omega, which corresponds to a periodic disturbance in your data. Okay, that's actually the on the angular frequencies, normalized angular frequency. This is pi radians. That will be somewhere in here. Noise, meaning that on the spectrum there is a peak here. For example, 100 hertz. You have a rectifier, full wave rectifier. It gives you 100 hertz humming, not 50 hertz, but 100 hertz. Why? Have you gone through this one on the signals? Why this one is usually on 100 hertz? Or in US it's 120 hertz. Well, the full wave, yeah, full wave rectifier, you know. So the first principle is 100 hertz. Easy. Okay. although when we have this chopper, the DC converting kind of things, then this can be anything and varying and ugly. But ideal case, you have a really nicely behaving linear power supply, and then you still have a little bit of humming because you have 24-bit A to D converter. 24 bits. You get down to microvolt levels. It's about 1 microvolt. The resolution. Yes, it's it's easy to get say a few hundred microvolt disturbances from your own designed linear power supply, and that's the good case. At least few microvolts. So how to get rid of that last bits? Well, you just simply put a 0 on that angle. Case solved, right? But the amplitude response looks like that. The question is how to get that one, the passband, back to normal. So it should look like this. Right. So you need to have some attenuation close to that same frequency. Amplification, which means that you will put a pole on the same angle as the 0. So you will get flat amplitude response and then infinite the attenuation on the stop and center frequency. In ideal case, yeah, everything works. And remember, I do not care about the phase response, which is really terrible with this filter. But, well, problem solved. Okay, problem solved, and even better. If we take a look at the half width of the filter, this distance here, as you can see, it's on frequency. That distance is exactly the same. Okay, I will just mark it A here. Small a. The minus 3 dB half width is basically same as the distance of this pole to unit circle. Ha! Pi. Okay. Remember the amplitude response, how it's calculated. The product form. So we have e to j omega minus z1 e to j omega minus z2, and these are actually the absolute values, and then e to j omega minus p1 e to j omega minus p2. Okay, it looks like the in this point, distance to Z1 is A. This is A. Okay, what else? This is Z1, P1, these are Z2, P2. The distance, these are about equal. So these here are about equal. Equal-ish. So that's 1. That part is 1. What is this part here? Well, actually, that distance. It looks like that is about the 90-degree angle. So this is square root of 2 times A. A square root of 2 times A, roughly. This is not science, this is technology. So we have square root of 2 times A, which means that this actually becomes 1 over square root of 2, which is minus 3 dB point. Ha! Easy! Magic! So what we need to do is to find first the what is our corresponding frequency in this relative frequency, omega n, and then just decide what is our half width of the filter and use that as the radius for the pole. The angle is the same as for the 0, but 0 is on the unit circle. So yeah, that's how you design a beautifully working bandstop notch filter. It works as long as we have a perfect world. Like this is really exactly on the same place. Okay, the narrower the filter is, less tolerance it has for the time jitter, either on your this disturbing noise signal. Well, if it's from the electric outlet, this is pretty good actually. I think it's 3 ppm or something like that. It's pretty constant. How about your microcontroller? It has about 5% the accuracy on the crystal frequency, unless you put it on Owen, an external oscillator on Owen. So basically heat balance it, then you may actually get into this a couple of ppms with good crystals. But anyways, the in perfect world it works. Okay, yeah, the same thing. Oops. There we go. Then about these classical filters, remember those from the analog electronics classes, the active filters, the Salinki structures. We have the Butterworth, which is flat, like that. Then we have Chebyshev, basically type 1 Chebyshev, meaning that we have some ripple on the passband, on that red curve. We can see some variation of the amplitude response on the passband. And then we have the elliptic, which is equal ripple on passband and equal ripple on stopband. Elliptic filters are quite hard to tune in real life, and not higher than, say, 4th degree can be done on analog systems, practically. On digital systems, well, actually next week we will take a look what happens to the computing accuracy and what you can do with in real life. Okay, but anyhow, yeah, I think I already mentioned at some point this zero phase filter, which is basically not a filter, but, well, it's not a filter design, but it's an implementation. So we just have to filter the data twice, first on forward direction of time, and then swap the direction of the data, run it through the system, the same system again, and then swap the direction back. Okay, that will take care of this any nonlinearity in phase response. Actually, it returns the phase shift back to 0. So group delay for this kind of system is 0, meaning that only for post-processing. But that's about 99% of the needs. Real need is usually post-processing of the data, except on control systems. Then you have real-time requirement. Okay, median filter. Just another filter, but just as a curiosity, how to get rid of spurious peaks on the data. So that's the most efficient way of doing it, simple to make yourself, and works really beautifully with this data, which has, say, normally single as usual, but then at some points it has, for some reason, it has spikes like that, which are not necessarily real. Well, glitches on the system, that kind of stuff. Or, well, you have A2D converter, but your software doesn't run correctly. You usually have something like that showing up. Wrong values, missing bits from the end, or missing bits from the beginning, or totally bogus, or a couple of values like 0x, F, 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 F. That's usually bogus. Let's see, 0x, A5, 5A. Anything that has A5s, that's usually also bogus. Okay. Yes? No. It's not linear. No, it does not have. But, okay, this is a special filter for special use. With any linear filter, you will have some remains of that one. And you basically, the problem with these kind of spurious peaks, it's wide spectrum. How you actually filter wide spectrum noise without affecting the noise itself. You really have to go in some sort of adaptive way. This is not really adaptive either, but this is a perfect filter for this kind of data sets. Basically, how to do it? You first order these values. So basically, we have the x1 to x5. You sort them. For example, there's this nice function qsort, quick sort in C standard libraries. And then you pick the median value. That's never the median. It's the highest value usually, or lowest value. It's never the median. So median value, actually, then you just replace it with that. Peak is gone. Okay, we altered the data. But as I said, this is not science. This is technology. This is how you get rid of those annoying peaks. On the single peaks on the data, not all the peaks.
How many samples do you take for the
okay, how long this window should be depends totally on the spurious peaks. If they are single peaks, 3 will do the trick, and that's the best actually to do. If you have a chance that there are actually 2 such cases on the same frame, then you need more. Then it's minimum is 5. So it totally depends on your data. And if it's astronomical data, never use it. You might actually just lose your fame on the stars. Yeah, the real signal, that was the some intelligent life form trying to reach us. There it goes. Yeah. Oh, by the way, there's a small planet. This is a planet. No, it's not a planet. It's one of those asteroids which are circulating the Earth. Its name is Piironen. My brother. Haha. Try to top that one. Well, easy, but But if you're a geek, it's hard to top that one. My big brother actually, he's infernal now. Passed away, but still name remains. Okay, so but anyway, so back to this one. Yeah, medium. What I'm talking about. So it's a non-linear operation. So low-pass medium filter reduces signal peaks from the signal. Okay, how about if you're looking for peaks, anomalies? Then use high pass medium filter, meaning you'll take the original data, subtract the median filtered one with the correct time shift. Only thing is remaining are those spurious peaks. That's also a nice trick. But again, it's about what you'll try to look from the data. If it's anomalies, single anomalies, what you're looking for, median filter is probably a way to find them. Okay. And then, of course, the biggest industry for this one is the 2D, meaning the image processing, how to get these, megapixel cameras cheap enough to put them on inside of mobile phone. You need to get rid of the dead pixels. How to get rid of the dead pixel? Well, media filter. For example, here I have this 4.4. The cell which has one single pixel is bad. We know it's bad. So what we can do, we basically just calculate the median around it and replace all the values by the median, and yeah. It smooths the data a little bit, but anyways, it's it works for dead pixels. Okay, back to the linear world. Have you ever thought of how a radar works? Yeah. Yes, you have. So there you basically have the matched filter. So in radar frequency, it's really hard to produce exactly the same power or same pulse form for every single pulse you send in radio frequency. That's a simple physics. So basically, if you take the filter coefficients by taking a sample of this transmitted pulse, then basically you have a perfect filter to filter the everything else but the signal, the returning signal on the receiver. So I think I have told you about that one already. So it's basically an FIR system, but still it's kind of a nice technology. So if you just bounce into the word matched filter, or you are dealing with any kind of radar technology, meaning, well, photodar, sound radar, wind profiler. Weisel has this triangular, this wind. Yes, that sensor. It's what is it? It has its own name. It's ultrasonic, the wind sensor. So that's where you use match filter. I don't know if they are using it, but at least I told them to do it that way. So it basically optimizes the signal to noise ratio. Yeah. So, and then some more, advanced topics. So a couple of things I'm leaving out from the scope of this is that currently the trend is going to this multivariate rate signal processing, meaning that we don't have a sampler and we have different time coming the unsynchronized data, and then we need to process that one out of the scope of this This is basically fundamentals of this digital signal processing. And what else did I leave out intentionally? Well, a lot of things. But that's why you have the all sorts of books. Okay, how to get back to the... All right, so that is the so-called theory part. Let me just to the MATLAB exercise directly. So today's exercise, or this week's exercise, is about I hope you can open this one, right? Okay, let I remember to share it. Sharing is caring. So infinite impulse response systems. And first is to design a band stop notch filter, meaning that one. Okay, plot zeros and poles. Plot first 25 values impulse response. Sounds like a quite straightforward task. Then we have this design an IIR low pass filter with the following parameters. Yes. I will show a couple of tricks there too. What else do we have? And comparing the filter, I would guess that the IIR filter, I already made a claim that, okay, we need less calculations to do IIR than a similar properties on FIR system. It's basically it's a simple mathematics here. Then design an IIR high pass filter. Okay. Could be done old school, meaning that we make the low pass filter, then transform it to high pass filter. Could be done, we are not going to do it. And design IIR filters that match the requirements you determined in exercise 4.7. I hope you got the 4.7 done. Haha. If you didn't, you may want to pair up with someone who did. All right. So, and the ones who did finish that 4.7 exercise have now an edge. Okay. It's called entrepreneurial edge. Okay. Comparing the filters again. Then design filters. Okay, then either IIR or FIR to match this kind of system, which is a simple tone adjustment. Yeah, and applying that one. You may freely choose your own sample, meaning anything legal will go. So don't take any, copyright material. Yes, freesound.org, for example. Yeah. Check the copyright disclaimer that but it's almost always, okay for educational purpose, or as long as you don't make any money. Okay. Anyways, so on educational purpose, nobody else is allowed to make any money than the teacher. Life is good. Okay. Yeah. I will start with the GNU update first. Okay, stop and the notch stop band filter and band stop filter. Notch. Okay, let me change that one. Band stop. Stop and band stop. Yeah. Filter. Okay, let me start with some system which has, for example, sample rate of 2000 hertz or samples per second, which is, say, quite typical number for a data logger. All right, then we have that annoying 100 hertz hum. So we have the noise frequency F noise, 100 hertz, line humming. And simply from this information, I can already start design. Okay, from 0 to pi, what is that angle there? So the corresponding omega noise is actually F noise times sample rate, times divided by the sampling rate times 2 times pi, because 2 pi is same as the sample rate, right? Okay, that's the omega in radians. All right, and then we can actually put already those zeros on their places. So that's actually the same as e to j times omega n. This is e to j times minus omega n. So z equals, for example, the first tier, one of them, say j times omega noise. This is the upper, the positive side, the 0, and then the other one. Actually, let's do it like this: zz semicolon conjugate of zz. So zz is actually the same as complex conjugate of the value. There we go. So now we have complex conjugate pair, and to make sure that they actually are on the unit circle, let me this must be done on Octave only because I'm lazy to change the start up see the file. Okay, now I should be able to take the Z plane ZZ. Oops. Yep. Okay. Yeah. 100 hertz. Right there. Good. This far. So next step is to find the what is on my minus 3 dB half width. I've just set it up. So how wide filter we would like to have. Maybe we don't want more than, say, 20 hertz both sides. If you start having wider, then you start losing some information. And again, this is not science. It's application-specific engineering. So half width, for example, 40 hertz. 40. Corresponding angle. So this is angle difference here, the A. So we calculate the same way as we did the omega. By the way, if you type few words first, letters, and then arrow up, you get the previous commands which started like that. So omega half is f half, like that one. I don't care the numbers, but that should be actually that distance, which is now the distance from here to unit circle. So this one here is 1 minus a. So I can calculate the poles. Oops. Poles are 1 minus omega half times ZZ. Well, if these are on the unit circle, then you just multiply it with the radius. You get on the same angle, but inside of the unit circle. So these are the poles. And I designed a stable filter because my poles are inside of the unit circle. Nice! Looks like a IIR filter, which may or may not do the trick. For that one, let's see, the corresponding the filter coefficients are the BB are the polynomial coefficients defined by the zeros, and AA are the polynomial coefficients defined by the poles. Like that. And basically, then we can do some filtering, or actually, sorry. Let's check the frequency response on new window. Okay, looks like we got more or less a filter that fits our requirement. Yep. So let me expand that one a little bit. So this is straight at 100 Hertz with lots of attenuation. Actually, it's infinite right at the 100 Hertz. But this is calculated on the locations which do not include that 100 Hertz. That's why it's a little bit short here. But anyways, you can also see, let's expand that part. My design parameter was for 3 dB point was the half width of 40 Hertz. Yep, it's about from here to there. It's about 40 Hertz. Yes, it looks like it works. The design works, but you also can see, okay, if the line humming was not at 100 Hertz, but a little bit off, like, say, let me expand that, but, yeah, 5% off, meaning that you are using, on microprocessor, you're using the internal oscillator, which usually have, say, few percent of accuracy. Say, cheaper it is, worse it is. So it's 5% is quite typical, actually, for small 8-bit microcontrollers. At 95 Hertz, you have only 18 decibels. Maybe enough, depending how much humming you have, but may not be enough, depending on the application. But at least you can say, I tried. Okay. Good. So that was the filter you can design by this simple placing of the notches, so-called. Okay. Then how to design a low-pass filter. The old-fashioned way would be, let's see, okay. So we take the analog system, but basically we can also call a function called, for example, Butterworth filter design. You just give the order of magnitude and then the cutoff frequency. It gives you a Butterworth filter. Okay, low pass, or then you can also type with high pass. The only problem here is to find the what is the order number. But there you can actually also use the but ord. Does it say anything about here? No, it does not. But there's also a pair for this filter design is the but ord, like Butterford, the order number. And what you give to that is some, well, you give the box. So you will give the, let's see, pass band, stop band, RP is pass band ripple. Okay, actually that defines which point we are using as our design point there. So that's the RP, and here we have the attenuation. Here is the RS. This is the WP passband and WS. So you basically give those parameters, design box parameters, and it gives you which order filter is required to basically to design based on the characteristics. So, for example, requirements for on the previous task. Let's continue and put, say, some low-pass filter so that we have. This is just an example. So that was 100 hertz. Then we have, say, 200 hertz to 300 hertz, 3 dB ripple. Okay, why not? And the say at least 60 dB attenuation. Okay. So equals 3 dB. RS equals 60. WP equals 200 hertz. Well, times, you know what, WS equals 300 hertz times, you know what. Okay, so what I could do is calculate this first. Oh, let's see. I need to check that if these ripples are positive or negative. I think, yeah, decibels, I think they're positive. Okay, RP equals 3, RS equals 60, WP equals 200 divided by Fs times 2 times pi, and WS equals 300 divided by Fs times 2 times pi. Okay, and then we just n capital N equals to buttered. In which order? WP. Fourth order. So it gives just the order number. But now we have easy task to just B AAB equals butter NN WP. I think that was the way to call it, was it? Yes, cutoff frequency. Good. And it gives me the perfect numbers for the A and B. That was simple. Only thing left to do is to actually check the frequency response. There. Ooh, wow. Maybe I should expand it a little bit. It seems that the what they are using is different scaling. But this is off by 2, meaning that. Wait a minute. Pi. I have pi extra. Okay. It also helps if you read the those manual pages. Okay. Sorry about that, since basically it gives. See, let's read it exactly what it says. Okay, frequencies are normalized to the Nyquist frequency in the range of 0 to 1. Yes, but that's probably the same for the that also 0 and 1. Yes, okay. Sorry about that, but well, it's not that badly off. It's just the pi off. Okay, now it's normalized correctly. I think this. Okay, then now we have 16th order, and there, and frequency response is okay, a little bit better. (200 hertz cutoff frequency). Okay, as you can see, it goes about that 6 dB per octave. Oh no, 6 times 8. So, but anyways, it has a lot of attenuation, and what you see down here on the frequency response, well, 500 dB. It's quite hard to calculate those values already. So this is how many zeros? A lot. So why it shows it like this is because of the calculation accuracy. It hits basically the machine epsilon here. Okay, so that's the old school. Geeks like me used to do this exactly same question 30 years ago, like that. Or actually, teaching 20 years ago was still current with this kind of tools, but we have better. So usually I'm not advertising anything, but I just mentioned that on real MATLAB, I need only one. I think I need only one MATLAB here. On real MATLAB, first of all, you can download a free trial version for 30 days with any kind of environment. There's a special environment for signal processing, digital signal processing environment, which has all sorts of toolboxes. If you get into the work that you need to do some DSP design, ask your boss that you can buy license to a professional tool that I'm not mentioning. If they say no, it's too expensive, then you ask how expensive it is if I spend 2 months instead of 1 day on this project. Okay. But anyway, you just open Filter Designer, which is a filter design tools. Oh, wow, it has that kind of box. The same low pass filter as previous. Yes, designer with capital D. Toolbox.
At least $2,000. If it's a fixed license, if you want a floating license, it's 10 or 15 grand in euros.
Yeah.
That's nice.
Yeah. We have the cheapest academic licenses in Europe, in Metropolia, for historical reasons. It's not campus license, but it's a classroom license, which MATLAB does not anymore sell. For obvious reasons, they want to sell the whole package. But it's unfortunately we need about 20,000 euro a year, which is annual. Oh no, 70,000 euro annually to have a campus license, which we don't have. That's about the same as the lecturer's annual salary. So who would you like to kick off? Hopefully not me. But anyways, so it's expensive. And that's basically, well, it's the free word. So, but anyways, let's go back to this business. So filter designer. And yes, for 30 days trial, you can get it for free. Then they have this student, the version which you can buy. It's not that expensive actually. Student version, I think. Yes. So if you are going to use it for the rest of your studies, maybe it's better to buy that compared to buying a mobile phone that you throw away. I don't know. All right, so you just start clicking. First of all, you can use the same variables as in MATLAB Workspace. So all of these values you can take from the MATLAB Workspace. F noise. Okay, that was 100 hertz, right? Stop band. I think that you can even put 2 times F noise. And then design filter. Whoa, FS. Didn't I have it? Oh, no, I didn't, since I have. I'm lazy. Okay, let's see. maybe first run it just like that. Oops, there's something missing. Oh, yeah, of course. It has this package load and such kind of things. These are not good for MATLAB. There we go. So I can actually do also these commands just for fun. Yeah, it works. Yeah, it looks like it works quite the same way as the Octave does. Good. It just looks a little bit better. Okay. Maybe even those. I'm not going to do those. They will mess up things. Okay, now I can actually go back to my. Now I have the FS right workspace. I have FS noise. Good. And I have a perfect FIR equiripple filter design. Or I have all the IIR filter designs what you ever want to have. Some types of filter. There's a Butterworth. Well, still the same old. Problem with the Butterworth is actually what you saw on this Octave window. So the problem with the Butterworth design is that it's basically losing. Well, where do we need more than 100 dB attenuation? So that's total waste of calculation power to get it down that way. Always, if you can basically have less of attenuation or more ripple, looser filter constraints, you don't need that many calculations. So basically, we can, in this design, go to some other, like, well, Chebyshev 2. Okay. So that basically has 8th order instead of 16th order. Hey, wait a minute. I remember something. Was it 200 and 300 were the design parameters on the previous? Yeah, 11th order. Or even less order by taking the elliptic, I think. Sorry. That's not even 60. Now it's about the same as on the on my Butterworth design, which requires lots of handwork and guessing. So this is a tool to use. Okay, 6th order, only 3 second-order sections. Okay, next week we'll go through about that one. What is the section? Sorry? Ripple. Yeah, we can. Yeah, yes, 3 dB. Yeah, even less calculations. Okay, and then you have the analysis tools also. So how about the phase response or group delay? Yoo-hoo. Impulse response. Ha! Oh wait. I shouldn't show this on you. Step response. So if you have an analog system, you can start comparing. Zero pole plane, of course. The coefficients on coefficients matrix. Okay, how to use this filter design. Actually, this a little bit about the structures, which is not today's topic. This is so-called direct for second order sections. So this design is based on that we have cascaded second order sections, meaning, well, you know what cascaded means, that we have those on the same line. So you have the first second order system, second order system. Actually, then you have the that first order system as a third parameter. If that's in really that's actually fifth order, because each of these second order system is implementing two poles and two zeros, for example those, with some additional gain. Okay, how to get it back to this, what we have already since the BBs and AAs. That would be the direct form type. Actually, then we need to, let's see where's the, yeah, there. Convert to single section. By default, all the filters should be defined as second order sections, especially these IIR systems, because the computing accuracy is much higher. But more about that one next week. So if you want to convert it to the single order sections, yeah, those are the coefficients, which you can then export to, who's it export? Oh yeah, export to workspace as coefficients, like numerator would be our BB, BBF, AAF, export. Now we can go back to the workspace and, for example, wait a minute, how many MATLABs do I have? One too many. So frequency response, BB, FAAF. Yeah. Okay. So that's how the filter designer actually communicates with MATLAB workspace. About the exercise, write the commands to generate coefficients here. You know how to make screen dumps from the FDA tool. Okay, you just take the this one, whatever I want to show. For example, if I want to see the amplitude response, or well, both amplitude and phase response, then you just take a copy of that graphics and put it there. If I want to see the parameters, you can take the copy of the whole design. It's just bits. It doesn't consume more energy than writing the answers by hand. Okay. So this is the tool to use, and you can play around with different kind of filters there are. Then one more thing about the 9th and 10th exercise. So this might be already something that has been covered by the electronics teacher. So have you designed any audio amplifiers? No. You haven't? Really? You haven't? So, what kind of geeks you will be. Well, hopefully not kind of geeks at all. All right. So anyways, so how to actually translate this one to engineering? On analog frequency space, meaning logarithmic frequency axis. That's 1 hertz, or let's make it 2 hertz, 20 hertz, 200 hertz, 2 kilohertz, and 20 kilohertz. Next one would be 200 kilohertz. So this is the whatever border diagram, right? Then you have the decibels. You have had border diagrams, right? Yes, you have. Maybe you should have. But anyways, logarithmic scale on frequency. Why? Because human physiology is logarithmic. When you double a frequency, it will be the next octave. Same note, but the next octave. Double that one, it's again the next octave. Okay, so this is how humans hear things. We don't hear anything here. We don't hear anything here. I don't hear anything here. Maybe here. Yep. So, yes, we don't measure anything there. So, and what kind of A to D converter do we have? Sigma delta. I wouldn't trust anything here. Low frequencies. Okay. So, how to divide these to 3 bands? Physiological bands, meaning low frequencies, high frequencies, and the middle frequencies. Well, that's how you divide them. This is a natural division. So in order to adjust the audio tone, you need 3 filters: low, medium, high, or bass, medium, and high. Although usually you have only for adjustment for bass and for high frequencies, because basically you have one knob that can be turned, well, up and also down, not just up, the volume. So basically we can pick, for example, middle frequency as the reference level, which is turned up and down, and then we have these 2 other bands here, and you start adjusting the volume by just putting a multiplication of those. So just adjust the gain, meaning that on the system level, you have a signal coming in, you have this filter bank, each of them have adjustable gain, and then you just sum the output. Low, medium, high, with gain high, gain medium, and gain of low. That's a 3-band equalizer, meaning the tone control of audio system. Nothing more than that. Okay, the rest of the parameters are there, and you can use, of course, the tools what are provided, meaning the FDA tool to design the filters, and then basically, then you can then use, for example, you know, that this is filter with some parameters, that's also filter with some parameters, and that's filter with some parameters. This is simply the linear gain. Just need to change from decibels to the linear gain values. All right, that was fun. Haha. 1 hour 20 minutes. Pretty good. Any questions this far from this topic? Yes. Mm-hmm.
If we have a really narrow bandwidth,
Mm-hmm.
then it means that we have to put the pole close to the units of circle.
Yes.
So it means it could possibly become unstable if we have.
Yes, exactly. That'll be next week. Any other things? Okay, start working. I will be here until 5 o'clock. But next I will go, of course, and get some coffee.